The lecture today is devoted to more information about electrical and electronic components for the purpose of realizing that just about any dynamical system can be built with these components. This is in a fairly sharp contrast with the mechanical elements, because it gives us an outstanding flexibility. It also gives us a preliminary view of what can be done by means of a computer. The usefulness of being able to synthesize just about any dynamical system becomes very real when we will talk about designing control systems. Indeed, designing control systems requires eventually their implementation, and electronics is a very good means of implementing control systems, or at least simple control systems. Today's lecture will be without the traditional notepad that I use, and will therefore be done by means of handwritten transparencies. You will see mostly my handwriting captured through the camera that you see here, and hopefully they will be quite readable. The camera is not excellent quality, and you will see some leakage. So let's move on to our lecture. For that, I first need to close this figure and launch this application again to propose a view from the top. So this is the view from the top, which I will maximize. Let's move the mouse, and let's adjust the sheet of paper. So again, we will talk about electronics, and dynamical systems. During the previous lecture, we have already seen how to realize pure gains. That is, V output is equal to a gain K times V input. We have seen how to do that using a combination of operational amplifier plus, in this case, two resistors. Now, we also have seen how to make a derivative. V output is equal to possibly a certain gain K times dV input dt. that required a resistor plus a condensator. We also have realized an integrator. The output is equal to the integral of the input, possibly preceded by a gain k. Again, this realization is done by means of an ampli-op plus a resistor plus a condensator. Now, in general, what we are interested in is replicating any transfer function we will not necessarily talk about the most elegant way of doing so, but we will talk about how to make it happen so that you know you can do it by buying off-the-shelf components and not having advanced knowledge about how to program. All I'm talking about today is doable by shopping at Radio Shack or Fry's, to mention some of the best known electronic shops around the neighborhood. So, let's move on and talk more about what we want to do. So, a transfer function can be seen as the following. A transfer function can be seen as the combination of in general a numerator divided by a denominator. Okay, we have seen several examples of such transfer functions by looking at arbitrary dynamical systems or arbitrary differential equation, and so far mechanical systems. We know from the theory of polynomials that we can write this transfer function as a1 s to the power p plus a2 s to the power p minus 1 all the way down to ap0 plus a sum of terms that look like AS plus B divided by S squared plus mu S plus K plus terms like this that will look like AK, or to change later, AM S plus B divided by S squared plus mu S plus K to the power N. These are like second order terms, plus first order terms, which will be more of the kind 1 over S plus lambda, where lambda is real. And by the way, so are mu and so are K. Or to be more precise, K1 over S plus lambda plus K2 over S plus lambda squared plus blah 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 plus Kn or M divided by S plus lambda M. Now there can be a bunch of these terms, okay? The numerator and the denominator may change in such a way that you have linear combinations of these terms. And therefore, we are left to computing things of the kind K times S to the power Q. Okay? Then terms of the kind K, terms of the kind AS plus B divided by S squared plus mu S plus K to the power Q, where Q is arbitrary. And last, K divided by S plus lambda to the power Q again, okay? And Q is arbitrary. So let's do just that. So let's just may say that we are interested in doing realizations. Okay? All right. So let us begin with again K. That we have done already. Okay? It is sufficient to do the following. We have V1 here. We feed into the negative pole of the op amp. We link the positive pole of the op amp to the ground. Hold on a second here. I made a mistake. We add a resistor here. We take, we divert that signal and we put a second resistor there. This one will be known as R1. That one will be known as R2. And we connect the two, so this one is known as R2, in such a way that we get, and I don't recall the exact formula, so I'm going to rederive them, but it is something like V2 is equal to R2 over R1 times V1 times minus 1. There is a sign flip. So we can rederive that by saying that the current going here is V1 over R1, and then sum the voltages across the armatures here to get V2. So with K is equal to R2 over R1 with a minus sign in front of it, we can replicate any K provided that we have lots of flexibility, which we do, with the resistors. Let me add, however, that this kind of K is negative. So the only way, or one of the ways that we can get positive K is by taking V2 and passing it through another op amp. We put it through a resistor R, which we hook to the op amp just like we've done before, and we do the same montage as before, except we repeat the same resistor, and we now obtain V3, where V3 is equal to minus V2,
giving us
the possibility of inverting the sign of K if needed by mounting this element and that element in parallel, in series, my mistake. Okay? Now this is not the most efficient way of doing that, but it sure is an acceptable way of doing it. Okay? And it can be built. Let me show you now how we can do a realization of the next element that we are interested in, which is a derivator. So we're going to look at s to the power q in general. We begin with an s. So we take v1 and we want to compute its derivative. For that purpose, we once again hook it up to first a condensator of capacity C, and second to our operational amplifier through its negative end. And we take the positive end and hook it up to the ground. We now hook, and we have already seen that, the input to a resistor R, which comes out and is connected in such a way that the output is V2. So, just like we have seen so far, we have that V1 and the voltage V across the capacitor must relate to each other. Now, how do they relate? Well, we have that the intensity satisfies the following: dV dt times C is equal to identity, where the identity goes this way. To be more precise, if identity is counted positive this way, the electrons charge negatively here, positively there. So we're going to use the other convention, that V is counted positively the other way around. And what we obtain is that V plus V1 must be equal to 0. Therefore, the identity is equal to C times minus dV1 dt. Now I flows through R as well, because remember, there is no current entering or leaving the operational amplifier. Therefore, we can write that V2 must be equal to, or V2 plus R times identity must be equal to 0 because of that circuit. Therefore, V2 is equal to minus R times identity. Now, there is a small error here that I would like to correct. Given the way things have been written here, okay, it is V minus V1, which is equal to 0, not plus. And therefore, I is equal to C times dV1 dt. Under these conditions, we obtain that V2 is equal to minus RC dV1 dt. And therefore, up to a sign flip, we can write that V2 is equal to, in the Laplace domain, is equal to K minus, or K, provided K is negative, times S V1. As a result, what we see is we can realize a derivative S a priori with an arbitrary gain K as long as it is negative. Bring on top of that our sign flipper, and we don't need, of course, what we do is we manage to connect our sign flipper to the the initial circuit that we have just described, and we get that the net result is we can realize any gain K here, including a gain of 1 or what. Now imagine that we connect this together with another of the same circuit. Then, instead of getting the output, which is at the end of the other circuit, is equal to Ks times the input, we will obtain, calling it V3, again connected with the ground, we will obtain that V3 is equal to K times K prime, the gain of the same circuitry, but maybe adjusted with other resistors, times S squared V1. Now what that means is that we can now realize a double derivative. And by the same token, you can extrapolate and say that we can realize Vn is equal to some number q times s to the power n times V1. Therefore, we can make a realization of arbitrary derivatives. Now, the same holds for the integrators. So an integrator realization, which is K over S, will be obtained by swapping the roles of R and C. And we get that the diagram now looks like V1. We still have an identity going here, a resistor going there, which we call R, and an operational amplifier, such that we keep connecting things. We put now a capacitor here with capacity C, and we link things together to collect the voltage V2 here. If the voltage V1 satisfies V1 is equal to R times I, as it should, because of the connection of the plus pole to the ground, then we get that I is equal to V1 over R. If we call V the voltage across the armatures of the condensator, we have that V2 plus V must be equal to 0 by going through that circuit, and noticing again that the voltage across these two armatures is 0. And last, we have that dV dt times C must be equal to the current. From this equality, we get that minus C dV2 dt is equal to identity, and therefore that V1 is equal to minus RC dV2 dt. Another way of saying it is that V2 is equal to minus 1 over RC times the integral of V1. Therefore, V2 hat is equal to minus 1 over RC times V1 over S. V1 hat over S. By the way, you may notice that I don't talk about initial conditions in all that happens, okay? So it is equivalent to say that all the circuitry is at rest at the beginning of the circuit operation. Now, guess how you can realize K over S squared? Well, you got it. You can just hook up the same circuit and you generate by putting this circuit and a copy of it with possibly a different C and possibly a different R in series, and you can obtain K over S squared, and by way of extension, K over S to the power N. Arbitrary integrators. So, this is, again, modulable, and we can flip the sign of K by using the flipping circuit that we talked about a few minutes ago. Now, we are interested also in realizing transfer functions of a more complicated nature. So transfer functions of a more complicated nature begin with 1 over s plus lambda. For the purpose of doing so, we will do a few experiments and try a few arrangements. One of them could be to do the following. With the same setup as before, we are going to use a resistor R here. We're going to again put a voltage V1, which is our input voltage, here. And we're going to link this thing again to an op amp of this kind, linking the other input branch of the op amp to the ground. Now, we will connect these things to a capacitor and to a resistor, which we'll call R2. And we'll hook this up to V2, the voltage at the output. Again, we have that I is equal to V1 over R1. So we know that the same intensity goes across the capacitor and the resistor. So if we call V the voltage across the capacitor and V tilde the voltage across the resistor, we first find that V tilde must be equal to R2 times I. Likewise, we find that V satisfies C dV dt must be equal to I. Okay, this is the standard equation for the resistor, and that is the standard equation for the capacitor. Now we get that V2 by summing the voltages across all the armature is equal to V tilde plus, so V2 plus V tilde plus V1 plus V, my mistake, must be equal to 0. Okay? Again, we use that circuit here that goes all the way to here. Okay? It's a loop. V2 plus V tilde plus V is equal to 0. Now, we can say that, therefore, that V2, so first we write that V is equal to integral of I over C from this equation. Therefore, we can write that V2 is equal to minus V tilde, which is minus R2 times I, minus V tilde, which is, so minus V tilde, minus V, and minus V is 1 over C times the integral of I over C. This is the 1 over C is already accounted for. Okay? We're almost done because V2 is therefore equal to minus R2 times over R1 times V1 minus 1 over C times R1 times the integral of V1. Now, do we have the desired result? Not quite, since we conclude that V2 hat must be equal to V1 times minus R2 over R1 minus 1 over R1C times S. Nevertheless, we have in fact found a way to get an interesting setup whereby we can take the sum of two transfer functions, one being a gain, the other being an integrator. Now, this is called a PI circuit, and fortunately, why? Because we call it proportional plus integral, and it turns out it is a very convenient circuit for the purpose of controlling dynamical system. It's just not the one that we wanted. However, there is still a lot of value to this circuit. So, of course, we're encouraged by what we see here. And maybe we could get something more interesting by swapping the roles of these two guys and seeing if we can realize some other convenient transfer function that sums two terms. So really here, I meant to be throwing the proper answer from the sky, but it's more fun to experiment and see what we get. It is more along the lines of what people actually do when they do research. So the last or the next element that we will study, and I will not claim what it is at the beginning since I don't seem to be able to do so, is as follows. We'll take the input V1, we will ground it, we'll hook it to a resistor and to a capacitor. A resistor R1, a capacitor C, and then we will do the same thing as before. Okay, we just draw the armatures. We just link that one to the ground. And we hook it up to a second resistor here, R2. And we collect everything at the output, V2. By the way, we can make these things happen. We will try and do so when I have the proper components handy. So what we get is that the intensity here still goes through that armature, so that once again we get V2 is equal to minus R2I by considering that circuit here, and which is a loop from ground to ground. Now we will talk about V tilde here and V there. We have that V1 must be equal to V tilde plus V. Now, dV dt times C is equal to the intensity I, dV tilde. So V tilde is equal to R1 I, and V1 is equal to V plus V tilde. The best way to understand how things go is we will rewrite this as dV1 dt is equal to dV tilde dt plus dV dt, noticing that dV tilde dt is simply equal to R1 di dt, and we rewrite this therefore as dV1 dt is equal to is equal to R1 di dt plus one over C times I, okay, where this one comes from this guy. Now let me try and finish on the same sheet of paper. If I go directly to the Laplace domain, I get that S V1 hat is equal to S times R1 plus 1 over C times I, or I is equal to S divided by 1 over C plus S R1 times V1. Therefore, giving us that and this is I hat, of course. Going back to V2 equals minus R2 R1, we get that V2 hat is equal to minus R2S divided by 1 over C plus S R1 V1 hat. This is called well, it's not called anything yet, okay? But we know that we can also decompose and do a partial fraction expansion in terms of saying that V2 will be equal to K1 plus K2 divided by 1 over C plus SR1 times V1. Now, what is this called? It's called a proportional plus lead controller. Or to be more precise, a proportional plus lag controller. Okay? And we will talk about it later. However, it is still not what we want. Okay? It's a combination of things we want, but not what we want. So we're going to try another element. Okay? With the operational amplifier. This time, we're going to take V1 at the input, possibly a resistor here, R1, and we're going to hook it up to the operational amplifier in such a way that we also have a generator here which puts a current or a voltage V2 across the armatures. And now we complete our diagram with R2, R1, etc., etc. And instead of calling it V2, we'll call it V tilde because I'd like to keep V2 here. So, if we're going to write this, what do we get? We get that V tilde plus V1 over R1, which is the current going here, must be equal to, sorry, let's do it again. The current is going to be satisfying V2 plus R1I, or V tilde, sorry, plus R1 times I must be equal to V1. Therefore, R1 times I is equal to V1 minus V tilde, and I is equal to V1 minus V tilde divided by R. Now V2 is equal to R2 times I. Therefore, V2 is equal to minus R2 divided by R times V1 minus V1 tilde. Now what does this do? That is like a voltage multiplier, or sorry, adder. Okay? Now the value of this is that, of course, we add or we subtract, okay? And we multiply by minus R2 over R1, or R. So we imagine that we can feed this guy with the output of one of our previous circuits, that guy with the output of another one of our circuits, and we can generate the sum of two circuits. This allows us, of course, we may want to use voltage flippers as a way to flip signs and transform this minus into a plus. Therefore, allowing us to add different elements and generate relatively arbitrary transfer function. Now, a way to get something with the course of the kind A over B plus CS might be to take this guy on one of the circuits, and on the other circuits, feed it through there in order to feed minus K1. Therefore, we would be left with K2 over 1 over C plus SR1 with this voltage adder here. We can actually combine this guy with a guy that just realizes this to subtract the two corresponding voltages and end up with this guy. Thank you.